Welcome to EDU World Space.
Note that the given coordinate system can be rotated about its axis until the line of acting of the range lie on one of the axes. Let's choose z-axis. This can be done because the range is independent of the coordinate system. It exists with or without the coordinate system. We only define the coordinate system to help us deal with vector operations. Changing the coordinate system only changes the components of the vector and the coordinate of the point. Also, it's important to mention that the real space is isotropic. Also, next we can rotate the coordinate system about the z-axis to get the line of action of the force to intersect the xy plane somewhere on the y-axis at the point A. Since we need to prove that it can be done, we only need to find one case and not the general solution. We can look at the task for help. We see that if we put the second force to act on some point on the y-axis, this problem look really similar to the one in the task 3.143. We only have additionally y component of the forces. Let's mark the point B somewhere on the y-axis and solve the system for the equation. Since the line of action of the force Fa is given, we have to find only the magnitude of the force to determine the force applied at A. We can write it down as Fa is equal to A lambda x, lambda y, lambda z, where lambda xyz are the factors of the unit vector that defines the line of action. Note that this value changes as we do the transformation of the coordinate system. We can write down FB as equivalent to Bx0 Bz. Since those two forces are equivalent to the original situation, we know that they must add up to the original force. So, A lambda x plus Bx is equal to 0. So, A lambda x is equal to minus Bx. A lambda y plus By is equal to 0. So, A lambda y is equal to minus By. And similarly for the z component, A lambda z plus Bz is equal to R. So, A lambda z is equal to R minus Bz. We also know that they must produce the same couple. So, we can write RA cross FA plus RB cross FB is equal to M. Solution of this cross products gives us the answer AA lambda ZI minus AA lambda XK plus BBZI minus BBX is equal to MK. Comparing both the sides, we get AA lambda Z plus BBZ is equal to 0 and minus a lambda x minus bbx is equal to m. Let's find b from the first equation and then put it into the second equation to get the magnitude of Fa. So from this we can get b is equal to minus a upon bz into r minus bz. And the further simplifications gives a is equal to minus m upon ar lambda x into bz. Returning this to the first equation, we get bz is equal to ar square lambda x upon ar lambda x minus m lambda z. This is the final expression for z component of the Fb. Now we can find the final form of the magnitude of the Fa by substituting Bz into the last expression for A. So A will be equivalent to Mr upon minus Ar lambda x plus M lambda z. We can also return the Bz into the equation for B to get its final form as well. So we can write after simplification B is equal to M lambda z upon R lambda x. All we have to do now is to find rest of the components of the Fb. So Bx is equal to Mr lambda x upon Ar lambda x minus M lambda z, and By is equal to Mr upon Mr lambda y upon Ar lambda x minus M lambda z. Let's write everything down. So we will get Fa is equal to Mr upon minus Ar lambda x plus M lambda z into lambda xi plus lambda yj plus lambda zk, and Fb is equal to R upon Ar lambda x minus M lambda z into M lambda xi plus M lambda yj plus Ar lambda xk. Sorry, it's Ar lambda zk, where the point B is 0 m lambda z r lambda x into 0.